We will start with one of the most common examples in machine learning coursework: house price prediction. You want to predict the value of homes in your neighborhood. You know that real estate appraisers use many details to predict value, such as the number of rooms and the house size. Therefore, even if you don't understand the relationship fully, you believe a relationship exists between these observable details and the house price. You choose to use machine learning to discover this relationship based on the data you have access to. Because you think you can find either the actual prices for homes recently sold in your neighborhood or generate accurate estimates for others by asking a real estate appraiser, you are working with a supervised learning task. Because you're trying to predict some continuous numeric value, you recognize this as a regression machine learning task. First, you do data collection. You collect numerous examples of houses which sold in your neighborhood within the past year and pay a real estate appraiser to appraise the house whose selling price is not known. Next, you do data exploration. You notice that all of your data are numbers, which is great, since most machine learning models operate on sequences of numbers. Finally, you do data cleaning. You look for things in the dataset such as missing information or maybe an outlier that you don't really care about in your problem, such as a mansion with 10 rooms. You know techniques exist to handle these cases, but for now, you choose to just remove these examples from your dataset. You might also plot house value against each of your input variables and observe that when either a lot size or room count increases, how the house value change. You split 80% of your dataset randomly into a training dataset and 20% into a test dataset. Okay, you're ready to try training a model. You do model selection. After exploring the data, you observe that the relationships between your input variables and label are pretty straightforward. When lot size increases, house value increases. You think this relationship is simple enough that you select a linear model to represent it. A linear model across a single input variable can be easily thought of as a line. It becomes a plane for two variables, and then a hyperplane in more than two variables. But thinking of it as a line with a constant slope will get us far enough in this example that we'll show it depicted here. To do the actual model training, you load your data in Python arrays and use a common Python library toolkit for training classical models. One of the most commonly used evaluation metrics in regression scenario is called RMS, or root mean square. The math is beyond the scope of this lesson, but RMS can be thought of roughly as an average error across your dataset. So you want this value to be low. In the chart shown here, you can imagine we want the line to be close to the data inputs. You compute the root mean square between your model's prediction of a data point and the true home value found in your dataset. You're still new to machine learning, so you're not sure how to interpret these results. You know that having an improved model will probably have a better RMS, but you're not confident if the specific value you have computed is good or bad. As a sanity check, you manually count how many predictions were off by some thresholds, 50,000, let's say, and determine that your model is pretty accurate within this range. You now use this model to predict the house value for other houses on the market. As you see in this example, we can pass any room count and lot size we want to predict the new home value.